Okay, snuck off to the bathroom and washed the ink off my hands so that we can restart at lecture 3.3, where we are going to talk about equations of state. Okay, so equations of state. All right, so now what we have, what we've done so far is we've come up with a unified standard way of thinking about our thermodynamic variables. In particular, we've talked about pressure and temperature and thermal equilibrium, right? So just a reminder, thermodynamic or thermal equilibrium is an important concept, right? It means that we've waited long enough. So we wait long enough after some kind of disturbance to the system that one, we have a uniform, constant Actually, let me just define this as equilibrium, right? So equilibrium is that we've waited long enough. So we can have a uniform constant temperature. And that's going to be a thermal equilibrium, right? But we could also be at rest with no unbalanced forces. And this would be a mechanical equilibrium. And we could have a uniform, unchanging composition and this would be chemical equilibrium. Okay, so now that we have this equilibrium, we can define if a state is in equilibrium. Okay, this is important. If a state is in equilibrium, then we can define an equation of state, right? We can define the state of the system. If the system is out of equilibrium, then therefore I cannot define the state of the system. I can't describe it with an equation of state, right? So we can define the state of a system with some number of thermodynamic variables. And the functional relationship between these variables is called the equation of state. I'm just going to make sure that you can see that. Check the camera here. Yeah, that's still visible. Good. All right. So we can define an equation of state. And what we mean is that there's some function, okay, some function which is a function of thermodynamic variables. For example, volume, pressure, temperature, density, something which equals 0. Wait, what? Equals 0? What do we mean by this? Okay. So it's going to be easier to think of this in terms of an example, right? So the example, equation of state, for an ideal gas. So that was PV equals nRT. But I could rewrite that my function, right, of P and V and T was PV minus nRT equals 0. All right? So my thermodynamic function is a function of these three thermodynamic variables. This is my equation of state equals 0. So what that means is I have three thermodynamic variables there, right? But only two are independent at any particular time, right? If I define the pressure and I define the volume, then the temperature is fixed. If I define the volume and the temperature, then the pressure is fixed. So there are not three independent thermodynamic variables. There's only two independent thermodynamic variables. So that's what we mean by that the function, the equation of state, equals 0. Okay? So we are only going to need two independent variables to define a thermodynamic equation of state. And we're going to use that concept many, many, many times in this class. So the two ingredients are, again, it's in equilibrium. If it's not in equilibrium, we can't define an equation of state. And that because the equation of state equals 0, that they're not all independent, right? We can have two of the three that are independent, or three of four that are independent, right? So this is the key concepts of the equation of state. We're going to use those many times, so you'll see it over and over again. Okay, thanks for paying attention. Have a good day.